Okay, sublimation. Sublimation is a transition directly from a solid to a gas, just skipping the whole liquid business. So here we have an illustration of ice. So we've got solid water. The water molecules are moving, but they're vibrating in place. They're staying the same relative to each other. Again, some have higher energy, some have lower energy. Now, the overall kinetic energy of the ice, because it's cold, is going to be lower than that of water, liquid water at room temperature, say. But still, some of these particles are going to have enough energy to escape, and they can go directly from the solid state into the gas state. That's called sublimation. The opposite of sublimation is deposition, which is going from the gas state directly to the solid state. So solid substances also have a vapor pressure, but it's low. It's a low vapor pressure. Sublimation usually occurs at a greater rate in an open container than in a closed container. Have you ever gone into the freezer and noticed that the ice cubes that kind of get left in the back of the ice cube maker or in the tray that maybe got forgotten and now they're small? They're smaller than they used to be. Have you ever noticed that? No? Yes? Some people have. How do ice cubes shrink? Water leaves, yeah. The water sublimes. So the water, some of the water molecules can escape from the solid into the air inside the freezer. What do gas molecules in the freezer do? They go in a straight line till they bump into something, right? And if the forces are strong enough in the thing that they bump into, they might get stuck or they might bounce off and continue being in the gas state. You've probably observed this. Ice crystals grow inside of airtight bags of frozen foods. I don't know about you, but you pull out a bag of old frozen French fries or frozen tater tots or something, and you dump it on the pan to heat it up, and you're like, where did all these ice crystals come from? Who in their right mind puts ice in a bag of tater tots? They didn't put that in there. Those ice crystals came because water in the tater tots sublimed. It couldn't escape because it's in this airtight bag, and so it ends up forming crystals of ice other places.
So does that mean that meat that has like crystals around it loses its tenderness?
Yeah, so it's called freezer burn. But anything that's not very well wrapped will lose moisture. And so then the texture changes and it's just not as good after that happens. So how can you avoid that? Well, a deep freeze is a freezer that keeps food colder than a regular freezer does. The colder the food is, the less sublimation will occur. The other thing you can do is to seal the food without any airspace. So if you take the meat and you wrap it in foil, which will compress nicely to the shape of the meat and prevent there from being any air spaces, and then put it in a plastic bag and seal it up, you can reduce the amount of sublimation that occurs. And that's how, especially if you don't have a modern freezer that automatically defrosts itself, that's where some of that frost comes from on the inside of the freezer. Some of it comes because every time you open the door, there's some air exchange with the room, and the moisture that's in the air gets in there, and then it'll crystallize on the side. But some of it comes from your food as well. Here's a picture of a lump of dry ice. So dry ice is solid carbon dioxide. We call it dry ice because it's cold, and you can use it like ice to keep other things cold. But it's dry because it doesn't melt. It goes directly to the gas state. It sublimes at room temperature but doesn't melt. So you can put it in a cooler with sandwiches or whatever, and it's not going to melt and get your sandwiches all soggy. So that's why when they ship like medicines and different things that need to be kept cold, they usually use dry ice because then you don't have water leaking as it melts, which, you know, anytime people are shipping things and liquids are coming out, that makes people very nervous, right? Okay, so let's talk about melting. Melting is also called fusion, and that can be a little hard to remember. So the way I remember that is I think about, well, what happens if you take a bunch of chocolate chips and you heat them up a little bit? They start to melt and fuse together, right? And then you've got this just big chocolate lump, right? They fuse together. Melting and fusion are the same thing. So if you take that block of ice and you increase the temperature of it, you warm it up, the particles are going to vibrate faster. And at some point, the melting point, they're going to have enough thermal energy to partially overcome those intermolecular forces and become a liquid. Now they're moving relative to each other, but they're still touchingly close. So we can look at a heating curve for that. So temperature, now here we're starting with water below zero. And as we heat up that ice, the temperature is going to go up. But once it begins to melt, the temperature is going to remain constant. Just like when we had the boiling water and the temperature remained constant. Because what's happening here is the more energetic particles are going into the liquid state, leaving the rest of them at a lower average energy. And so the temperature doesn't rise until all of the solid has melted. If you put more heat into it, it will melt faster, but it will still melt at the same temperature. So, you know, here I have my rock star with ice in it. I can tell you what the temperature of that is. It's pretty darn close to 0 degrees Celsius because there's water and ice together. And anytime you have the liquid with the solid, the temperature is going to be the melting point of that substance. So we've got melting or fusion is a transition from solid to liquid. Freezing is the opposite, from a liquid to a solid. Of course, there's energy involved in this too. Melting is an endothermic process. I think we understand this. How do you get an ice cube to melt? You heat it up, right? You put heat into it. So how much heat do you have to put in? Well, that's called the heat of fusion. Heat of fusion, heat required to melt 1 mole of the solid. So for water, that's 6.02 kilojoules per mole. Notice that's a lot smaller than the heat of vaporization, which was 40.7, 6.02. So melting is endothermic. That makes sense to us. Freezing is exothermic. When you freeze something, it gives off energy, gives off heat. That doesn't seem right, does it? That always bothers me. But it's the opposite process, right? If you melt something by putting heat into it, how do you freeze it? You take heat back out of it. That's what your freezer's doing. It's got that motor and the compressor and everything, and it's sucking heat out of the inside of the freezer.
So freezer and fire are both exothermic?
Yes, freezing and burning are both exothermic. Yeah, kind of makes you think about things. So in Fresno, you might not be so familiar with this, but I live in Reedley where we have a lot of citrus fruit. And citrus in the winter, there's always worries about the temperature getting too cold. If the temperature gets below about 26 degrees Fahrenheit for like 6 hours or so, maybe it's 4, the oranges freeze, the lemons freeze. Yeah, so we've got a bunch of ways to compensate for this because the orange doesn't freeze at 32 degrees Fahrenheit like water does because it's got a lot of sugar in it. And we'll talk about that later, but that changes the melting point. But around 26 degrees, it will freeze. So you have to keep the temperature above that. Well,
frozen oranges that are like not tasty at all.
Frozen oranges are nasty because the freezing messes up the cell structures in there. It breaks all the cells and they get mushy and nasty and they rot. And yeah, it's devastating. It's devastating to the economy. It's just really bad all around. So one of the strategies that they use is they water the fields when a freeze is predicted. So how the heck does watering your field, flooding your field, help? Well, you've got all this standing water in the field. The temperature drops. The water begins to freeze. As the water freezes, it's actually releasing some energy and keeping the temperature where the water is freezing at 32 degrees Fahrenheit, 0 degrees Celsius. The temperature there will not drop below that until all the water has frozen. And then you bring in some fans, these big wind machines, to help move that air around, and you can keep the temperature of the oranges above 26. So chemistry saving citrus fruit.
What if you watered it with hot water?
What if you watered it with hot water? Well, if you used water that was too hot, you could damage the roots of the tree, so that would be bad. I don't think the temperature of the water would really have that much significance. Yeah. And yeah, you could, put big propane burners out there or something, but that's going to require an awful lot of energy and not really do that much good. But watering the fields, it's all set up to be watered anyway. And so that's a plan that's been pretty effective. So I think that's cool because that applies to life in the Central Valley. Heat of fusion is usually much less than the heat of vaporization, and that's because in order for something to melt, you don't have to completely break the intermolecular forces. You just need to partially break them so that they can slide around each other. They don't have to become completely separate. So here we can look at, here are some heats of fusion for different substances, and we see that the heat of fusion for water is higher than for alcohol or acetone, but actually diethyl ether has a pretty high heat of fusion. This table's comparing heat of fusion with heat of vaporization, and we see that without exception, the heat of vaporization is much higher because you have to actually break all the intermolecular forces for it to escape into the gas state.